Hi, I'm Patty Schwarzkopf. Today I'm meeting with one of my students to take a further look at functions. First, we'll graph functions, looking for intervals on which the function is increasing, decreasing, or constant, and determine relative maxima and minima. Then, given an application, we'll find a function that models the application. Once we've found it, we'll find the domain of the function and function values, and then graph the function. Finally, we'll graph functions defined piecewise. Now, functions occur in so many real-world applications that it's important that you're able to analyze them. Let's begin by talking about the graph of functions. Now, when we read a graph, we read it as we read a book. We read it from left to right. On a given interval, if a graph rises from left to right, it's increasing on that interval. So we would say that this graph, assuming that it continues in this way, is increasing on the interval -infinity to a. If it's falling from left to right, it's decreasing on that interval. So for this particular graph, we would say that this graph is decreasing on the interval from b to infinity. If the graph stays the same from left to right, it's constant in that interval. So we would say that this graph is constant on the interval a to b. Now, one thing to remember is that all these intervals we're talking about are open intervals. Let's take a look at a problem. Determine intervals on which the function is increasing, decreasing, and constant. Now, we can see that the graph stays the same on the interval -5 to 3, so it's constant on the interval -5 to 3. I'm sorry, -5 to -3. We see that the graph rises on two intervals. They're -3 to -1 and also from 3 to 5. So which term would you use to describe the graph on these two intervals? Would you say increasing, decreasing, or constant?
Since the graph is rising, it would be increasing on those intervals.
Good. So we would say the graph is increasing on the intervals -3 to -1 and on the interval 3 to 5. Now we see that the graph is falling on the interval that remains. And what would you say here?
The function is decreasing on the interval 1, 3.
Good. On the interval from 1 to 3, the graph is decreasing. All right, good work. Now, in many real-world situations, it's important to find a maximum or a minimum value. When we view a graph, each high point gives us a relative maximum, and each low point gives us a relative minimum. Let's look at this in a more formal way. Simply stated, f of c is a relative maximum if f of c is a high point in some open interval, and f of c is a relative minimum if f of c is a low point in some open interval. So let's take a look at an example here. Here we have a graph of a function that we'll call f of x. F of c sub 1 and f of c sub 3 are relative minima, and each one is called a relative minimum. Together they're called relative minima because they represent low points on the graph. And f of c sub 2 is a relative maximum. Remember that relative maxima and minima are the y values of the relative maximum or minimum points on the graph. Let's take a look. Using the graph, determine any relative maxima or minima of the function f of x equals 0.1x cubed minus 0.6x squared minus 0.1x plus 2, and intervals on which the function is increasing or decreasing. Let's look at the graph. Here's the graph of the function f of x equals 0.1x cubed minus 0.6x squared minus 0.1x plus 2. And we see that we have two extreme points. We have an extreme point at negative 0.082, comma 2.004, and we have an extreme point at 4.082, negative 1.604. So what we need to determine is what the relative maximum and what the relative minimum points are. So is the relative maximum or the relative minimum the x-coordinate of the extreme point or the y-coordinate?
I'm pretty sure it's the y-coordinate.
That's right. It is the y-coordinate. So we would say the relative maximum is 2.004 and the relative minimum is negative 1.604. Now, many real-world applications can be modeled by functions. Let's take a look at an example of this. The sound shop has 20 feet of dividers with which to set off a rectangular area for overstock. If a corner of the store is used, the partition need only form two sides of a rectangle. So express the floor area of the storage space as a function of the length of the partition. Okay, let's begin by drawing a rectangle that represents this situation. Okay. Remember that a corner of the store is used. So if we have this being one corner of the store, we're forming a rectangle within that area. So we're only using two sides of our own dividers, and we have 20 feet of dividers. What we need to do then is to express the floor area as a function of the length of the partition. So what we'll do is to let x equal the length of the rectangle. And we'll label that. So we have labeled x. How would you then represent the width?
Well, there's 20 feet of dividers altogether, so the width would be 20 minus x.
Okay. So we would then have 20 minus x equals the width. Of the rectangle. And it's a good idea to label your drawing. So we have 20 minus x here. So let's play around with this a little bit. Suppose we let x equal 12. Then 20 minus x equals 8. So if x equals 12, 20 minus x, or 20 minus 12 equals 8. The area then would be the length times the width. The dimensions of the rectangle would be 12 by 8. So the area would be 12 times 8, or 96 square feet. Suppose x equals 14. Then 20 minus x equals 6. 20 minus 14 equals 6. So the dimensions of the rectangle would be 14 by 6 feet. Okay, we should put feet up there as well. So the area would be 14 times 6, or 84 square feet. Now we want to find the value of x that gives us the largest area. So what we'll need to do is to come up with a function that represents the area. So if we let a of x equal the area of that rectangle, when the length of the rectangle is x feet, then we would have a of x equals the length, which we define to be x, times the width, which we define to be 20 minus x. And we can simplify this. So we would have 20x minus x squared. Now let's find the domain of this function. What can you tell me about the values that x can take on?
Since the rectangle's length must be a positive number, and we only have 20 feet of dividers, x can only be between 0 and 20.
Very good. That's a nice analysis. Remember, our function was a of x equals 20x minus x squared. And as Amber says, we know that the dimensions have to be between 0 and 20. Since we're measuring a length, we have to be positive. We have to have a positive number. And the value can't go over 20 because we only have 20 feet of dividers. So we would say then that the domain of A is the set of all x such that x is greater than 0 and less than 20. Now let's look at the graph. Using the graph shown below, determine the dimensions that maximize the area of the floor. Now this is a graph of the function a of x equals 20x minus x squared. And we want to find the maximum area. Well, the maximum area would be 100 when x equals 10. So we would say that we want to let x equal 10 and 20 minus x equal 20 minus 10, or 10 feet. So we would say that we want the length to be 10 feet and the width to be 10 feet as well. Okay, remember x defined your length and 20 minus x defined your width. So we have 10 feet for the length and 10 feet for the width. So we want the dimensions of that rectangle to be 10 by 10, and that would give us a maximum area of 100 square feet. Now sometimes functions are defined differently on different parts of the domain. We say these functions are defined piecewise. Here's an example of a function defined piecewise. We have f of x equals x plus 1 for x less than or equal to negative 3, f of x equals negative 1 for x greater than negative 3 and less than 4, and f of x equals 1/2 x for x greater than or equal to 4. So what we're going to want to do is to graph this function. And what we'll need to do is to graph this in 3 parts. First of all, we're going to graph the function f of x equals x plus 1, and that will be the graph of a straight line, but only on the interval from negative infinity to negative 3. So for any values of x less than or equal to negative 3. We want the function f of x to be negative 1, which f of x equals negative 1 is a horizontal line at the height of negative 1, for x greater than negative 3 and less than 4. And f of x equals 1/2 x, which is a straight line, for x greater than or equal to 4. So let's see how this works. Okay, so we want the graph to be x plus 1 on the interval from negative infinity to negative 3, including negative 3. So what you might want to do is to look at the end point of that interval, which is negative 3. So we're looking at f of x equals x plus 1. If you replace x with negative 3, we would have a value of negative 2. So when x equals negative 3, we have a value of negative 2. So I'll put that here. So this is the ordered pair, negative 3, negative 2. And you can choose some other values of x that are less than -3 to help guide your graph. For example, if x is -5, -5 plus 1 is -4. So we would have the ordered pair -5, -4. And I know that in that region, the graph is going to be a line, a straight line. So I can just draw that at this point. And you could have chosen another point. For example, if x is -4, then y would be -3. Now let's graph f of x equals -1 in the region, or in the interval, -3 to 4. Now that's an open interval. The graph of f of x equals -1 is a horizontal line. Y equals -1. We're looking at that in the interval from -3 to 4. So I'll put open circles because it's an open interval. And we have the horizontal line in that region, in that interval. And now we're looking at f of x equals 1/2 x on the interval 4 to infinity, including 4. So I'll put that endpoint in. If f of x equals 1/2 x and x equals 4, 1/2 of 4 is 2. So we have a point 4, 2. If x is 6, 1/2 of 6 is 3, so we have a point 6, 3. If x is 8, 1/2 of 8 is 4, so we have 8, 4. And I can draw that line. So we see that our piecewise function has a graph that is in pieces. We have 3 pieces here. All right. So this is a graph of f of x. Now, one piecewise function of some importance is the greatest integer function. And it's defined in this way. F of x equals the greatest integer function, which is the greatest integer less than or equal to x. So, for example, if x equals -4, the greatest integer function tells us that the value of this function at -4 is -4. This is the greatest integer less than or equal to this number. Suppose x equals -3.6. The greatest integer less than or equal to -3.6 is -4. Suppose x equals -3 1/4. The greatest integer less than or equal to -3 1/4 is -4. So all of these x values have the same y value. So we would say that in this notation, the greatest integer value of -4 is -4. Greatest integer value of -3.6 is -4. The greatest integer value of -3 1/4 equals -4. Let's look at a few more of these. Suppose x equals 2. The greatest integer less than or equal to 2 is 2. Suppose x equals 2.1. The greatest integer less than or equal to 2.1 is 2. Suppose x is 2 3/4. The greatest integer that's less than or equal to 2 3/4 is 2. So all of these x values have the same y value. So we would say the greatest integer value of 2 is 2. Greatest integer value of 2.1 is 2. And the greatest integer value of 2 3/4 is also 2. All right, you get the idea. In a more formal way, we can define the greatest integer function as a piecewise function in this way. F of x equals the greatest integer function, which equals -3 for any value of x that is greater than or equal to -3 and less than -2. -2 for any value of x that's greater than or equal to -2 and less than -1, etc. the value of the function is 1 for any value of x that's greater than or equal to 1 but less than 2. The value of the function is 2 for any value of x that's greater than or equal to 2 and less than 3, etc. And the graph of the greatest integer function looks like this. And you can see that for any value of x, for example, between 0 and -1, the value of the function is -1. For any value of x between -1 and -2, the value of the function is -2. So you can see how the graph relates to the piecewise function we just defined. Now today we talked about functions and their graphs. It's important to be able to read a graph and to analyze it. You should be able to use terms such as increasing, decreasing, constant, and you also should be able to find relative extreme points. You should, and related to that is relative maxima and relative minima. It's also important to be able to work with piecewise functions. Make sure to review all that we've talked about today and make sure to complete all the exercises so that you become more comfortable with the material. Good luck with your work.